famous scientist. And it isn't like that. You know, ideas get produced irrespectively of the tools you use. There are good ideas, and there are actually, if you think about it, welcome. If you think about it, did Darwin need any mathematics to come up with his theory of evolution? Now, Darwin is often cited as the most important scientist of all time. He competes with Newton and Einstein, of course, but look, I mean, ideas come from thinking. It's the creativity question from yesterday. So, why did I go on that path? Why did I go on that path? Where? Can someone pull me back into the main thread of... Oh yeah, physics envy and simplification. The systems engineers in the crowd will know this very well. Could you come up with an equation like this that describes the internet? No. It's a machine of some sort. You can't do this either with the human body, let's say, or any life form. You can't compress it like this. It's just impossible. You have to have a list of causal factors that are of very different types and different dependencies. So you have a long list of dependencies that are way larger than the let's say, few dependencies between these, depending on how you count. So studying systems is not the same as studying physics. And again, probably we figured this out because it's the simple stuff. We have this, there's a famous cybernetician, Heinz von Forster, who said, the hard sciences are about the soft questions, and the soft sciences are about the hard questions. And I totally agree with that. Let's see, what is here? Yeah, so this is just, this is a slide about methodology. So I will talk a lot about methodology, and the reason I talk a lot about methodology is because in order to prepare yourself for what I will show you in the last two sessions, when I present the AERA system, you're going to have to be prepared that your normal way of thinking about systems may not work so well. And I'm really talking about a different methodology, a different way of thinking. It's more like biology, and we'll get into that. And we asked this question yesterday, intelligence, what is it? It's nature's way of dealing with complexity. This is just an attempt to, again, as Pei said yesterday, there's a lot of ways to look at intelligence, of course, and levels of detail and analysis and so on. This is starting from nature and starting with the example, the prime example that we have, humans. I can't help but coming to this point as an excellent starting point of an analysis of this kind. And also, you'll have a hard time convincing me that intelligence is not there for the real world. That is, the real world or environments of equivalent complexity. So, if you think of, let's see, human IQ, excuse me for using that concept, is here, and you go back, here you have, say, an amoeba. As I said yesterday, most people will agree this is an example of intelligence. Okay? So we can all agree humans represent an example of intelligence. Okay. But in nature, the further back you go on this scale, the more and more people will say, okay, no, stop. That's not intelligence anymore. And people don't have too hard a time of maybe drawing okay, this is where I'm getting dubious, this is where I'm absolutely certain. Most people will have their dog here and the horse. Then in here you have fish and stuff, and below this is, So, in this range, if we just talk about that, you've got, and even further down the line, even amoebas deal with very complex environments. So possibly the whole range here is vastly more complex environments than any computer system has to deal with to date, any AI system. You could say, well, okay, the Roomba vacuum cleaner, maybe it's dealing with the real world because it's situated in houses, and houses are the real world, right? Yeah, but it's missing so many things that we would be looking for in an AGI that is not even worth talking about. So one thing that comes out of this, and excuse me again for repeating myself a little bit here, but these are very critical things. They absolutely affect the design of these systems so profoundly that I can't help myself but going through them a bit again. This grounding of in the real world. So now, just to say this a little bit differently than yesterday, computer science basically gives you tools. The typical tools of used in software development are, you've got pipelines, you've got stacks, you've got FIFOs, and so on. And the way that software, as we know it from everyday use, deals with time is that, well, hopefully, the page will load, or hopefully it won't take too long to save this document, even though it's really big, and so on. And if you're lucky, you get this window that says cancel on it while it's saving or loading or whatever, because why is that important? Why is it that programs that lock us out and they just freeze up and they're doing their thing and don't give us any information or any way of interrupting it, why is it that so annoying? Well, it's because we don't have a clock on the wall here. It's because of the clock on the wall. It's because time moves on, and this is a key principle of life, in fact, that life moves on. Even if you don't have the time to think about that tree falling on you, well, that would be fatal. So time moves on, and this is a fundamental feature of AGIs, in my mind, of any proper model of intelligence. And therefore, we can't just borrow what computer science gives us or traditional AI gives us, because traditional AI, by and large, if you read any paper in AI, you'll have a hard time finding any mention of time. It's very strange. Even in planning, and this is partly because of physics envy, because people are so mesmerized by math thinking that they think, well, math doesn't deal with time, and Turing machines don't deal with time. Yes, there's the halting problem, but it has nothing to do with a real-world clock. So why should I think about time? I want to be mathematical. I want to be a real scientist like physics. So I'm just going to use the coolest math that's out there, whatever it is, and it doesn't deal with time because there's no real good math that does that. And so people just ignore this major feature of intelligence. Why do they ignore it? Because it's really hard. Well, especially hard if you come into a field that's not been dealing with it at all, pretty much, and you're the one who needs to figure it out. Well, it's much easier to just jump into what everyone else is doing. So, let's see. Okay, we did this one. All right, so we've talked about some requirement yesterday of that we need for an AI, for an AGI, but pretty much it boils down to this. Intelligence is a complex system. The standard methodology assumes, I'm going to go a little bit more on this topic here. The way we implement AI systems is by hand. How do we implement machine learning systems? How do we train them? We train them by hand. How are the good training examples and bad training examples collected? They're collected by hand, by humans, by the designer of the system. Constructionist design methodology is what I call this. And it's based on the divide and conquer methodology from science. So you're up against an argument there that's basically, if people have read their science, philosophy of science properly, they're going to be pretty good at justifying and trying to defend why we don't need a new methodology, why this should be just good enough. Now, I need to inject here a little bit more detail on this argument, because I'm not saying that divide and conquer in general is a bad idea, or even a bad idea for AI or AGI. What I'm really saying is that divide and conquer done the way it's been done in AI traditionally, that is by cutting out major features of intelligent systems. And actually, time is a good example of that. Then you will not understand the system that this is. It's a system, and it's like saying, well, we're Martians, we're coming to Earth, we're studying the internet, but we're not going to study the cables. Anything that's long and narrow, we're just going to ignore it. You'll see, of course there's some progress. These Martians will make some progress in understanding the internet. But it's very likely they will miss the major point of the internet, which is to send information from place to place. Oh, don't get me wrong, they'll figure out a bunch of stuff about the internet, you know. They'll see the routers and they'll see the machines and, you know, they'll know a bunch of it. They'll write whole documents filled, they'll have universities that, you know, talk about that stuff. Oh, but they never studied the cables. They kind of know about them, but either they ignore them or they think they're not important. So what we really need is to think very carefully about how we apply divide and conquer. Because obviously I'm not saying, oh, we're just going to do it all at once. I'm going to sit in a room for about 30 years and then I'm going to come out an old man. I'm already an old man maybe, I don't know. And I'll have AGI figured out. You know, it's just going to come all at once. That's ridiculous. It's going to be piecewise. It's going to be divide and conquer of some form. So, but the main message to take home from this is that all AI methods to date, because they come from Turing, I'll just take this one. It's not just time, but I'll take it. It's just such a major, major thing. I'll take time, and because Turing ignored time, and because Turing is the founding father of computer science and the computational way of thinking, you'll see a lot of kickback when you say Turing machines are an inappropriate way of thinking about intelligence. If that's the only way you think about it, okay. it's not a bad starting point, but it's insufficient. That's the problem. And what we really need are equations like this. Like, okay, so if you compare this formula to a Turing machine, if Einstein had left out, so like let's say we take out time, well, the speed of light. Okay, so you take that out. What's left? Well, E equals m. It's worth nothing. It's like it's worth something. It's worth. It's meaningless.
C squared's a constant anyway.
Doesn't matter. It ties to something physical. You see, you're already doing that mistake. You're basically thinking of the math, and you think, oh, no, it's the connection to reality. So yeah, this is how people think in computer science. They don't connect the math to reality. This is the problem. That's why physics is a superior science. I can't look at that like this. I have to have it properly. Okay, so. So this is the problem. We don't have this equation in computer science. But if we had, I think AI would be in a much better place and we'd be much further along. Well, I've got a list here of things that have been affected in a bad way by this. You haven't heard about behavior-based AI. Have you heard about subsumption architectures? Anyone? Okay, good. Three, at least. Everything we have today is essentially a constructionist design methodology-based system. Now, not very many people have thought about this. At least not of my colleagues. I ask them, the way in which you are studying your subject, how long do you think it'll be before you reach, the next milestone or the next 5 milestones? You can ask people this. You can ask them to say, what are the next major milestones in your field? Pretty much most people have a decent idea of that, and pretty much there's an agreement on at least like the top 5. Not in how long it will take to get there, but which one they are. So, for example, if you were a biologist, you're trying to figure out how the blood carries oxygen. You're looking for something like the red blood cells. Okay, the next major milestone in biology at some point may have been to figure out how oxygen is carried through the blood. And maybe you probably have some theory about that it matters that blood carries oxygen. Okay, that's I think that probably was known before. So that's a milestone. But now ask people in AI this. How long with the current methodology do you think it'll take to get there? Okay, well, they might be able to conjure up an answer like, well, maybe 5 or maybe 10 years. You ask them, do you think there's another way of doing it that would get there faster? Now, remember, this is a milestone. So you've got a mountain, you've got a flag here, like to use that, oh, it's a cross. Anyway, it's the Icelandic flag. You've got this mountain here. Okay, you're saying with method X, you can go like that, and you can reach the top. Based on where we are now, and I think we're here now, I say it's going to take at least 10 times as much, so it'll be sometime in 2025. So, people will be able to tell you this, but you can ask them, okay, is there another way to get there? I haven't thought about it. But in AI, people, even one of the founding fathers of AI, Marvin Minsky, is quoted oftentimes as saying, when people ask him, how long till we have AGI, he'll say, between 300 and 300 years. That's a huge margin of error. Of course he's going to be right, pretty much, barring World War III or whatever. My feeling is that with the right methodology in AGI, we could maybe speed up progress tenfold easily, possibly 100 times. I don't have the calculations for that. This is almost just like Marvin's answer, 300 to 300 years. It's a very rough guesstimate based on what I've seen so far. But if it's true, it's definitely worth a few years figuring out if there is such a methodology. So what we've been doing is essentially manual construction. People design algorithms by hand with their brain. Then they implement these algorithms by hand using programming languages designed for humans to write algorithms and run them on these kinds of things. Now, what you end up with is something, architecturally speaking, because, again, we'll come back to this word a lot, architecture, because what we're trying to understand is the operation of an architecture. So they will come out of this with architectures that look pretty blocky. It's not a coincidence that the most popular way of connecting people, connecting computers that are in separate locations is through an architecture called client-server with only two entities. And it took decades before what I was called peer networks really came on the scene strong. Simplification. Is this anything like society? I don't think so. I think society has a lot of communication networks for which the client-server model is just going to be a real mess. So, who here has written software programs that, say, ran on 2 or 3 or 4 separate computers and had to all communicate in order for the system to work properly? 1, 2, 3, 4. So you will know what I'm talking about. We try to simplify these connections as much as possible when you design the architecture. You know, if you can get away with just crossing out that connection by moving some function from here to there, you will do it. The reason is that this kind of a setup, when you have even a grossly modular setup with a few modules, this creates dependencies. Now, what is it about these dependencies that is so important? Let's say these are just wires. This is internet connection, okay? What is it about these things, these connections, that makes everything so messy? Time. It's because it takes time to send something from one place to another. And it's because, yes, you can synchronize clocks on these machines to within some error that's a function of the speed of your network. If your network is faster than the architecture's smallest atomic time step, you're in luck. Excellent. Because then your architecture may take 3 or 30 cycles of sending information back and forth. And you're fine. You can send the information, then you can ask for a check. Did you get that message? Then the other guy can say, well, yes, I got it. Here's what I got. Is it correct? And you can send back. And this guy can say, OK, it looks right. And you can even do that 16 times, maybe, if it's double or whatever. Whatever you need to do, you can verify that your architecture is actually, that the modules of your architecture are actually getting the information they're supposed to get. But we're not making, and that's fine if you're doing stuff like laptops and Ethernet in a world where networked computers don't exist yet, and you have nothing, and now you have some digital connection that's better than nothing now. That's fine, but that's not what we're doing. So why should we take the methodology from computer science wholesale? Even systems engineering, it's just not good enough. It doesn't deal with this thing properly. There are no programming languages that really do it. There was one attempt in the late 80s or mid 80s, I think. Does anyone know how to program in Ada? Ooh, cool. Excellent. A little bit? Okay. Why didn't this take off? I don't know. Somebody explain this to me. Because it was an attempt to do a programming language that handled time better. One of the motivations, of course, was a pretty sinister one, because this was funded by the US military, and they just wanted better killing machines, probably. So we're back to ethics again. But anyway, this is what you end up with, grossly modular systems. You have big black boxes. In some cases, they're actually black. And you spend an enormous time back and forth sending stuff, checking stuff. It's just horrific. Now, it's not horrific if it gets done what you need to get done. And that's it, then it's fine. So I don't care really how many acknowledgments my router sends to a server somewhere in the US or whatever. If it does, if I can have a sandwich while it's downloading the thing, it's fine. I can work around it. But that's not the kind of situation here. What we need to do is understand a natural phenomenon. And we need to use software. This is all we have, really, that is properly geared for us to study this phenomenon, intelligence. And there's a lot of, there's been a long time since software really came in full swing on the scene. Probably everyone in here started to do some programming, or could have, before they were 10. So it's not like, we've been waiting for this forever and now finally software system. There's a lot of history of software. It's just not functional for what we need. So we need to really get rid of the ways in which we've been trained and think of it in a different way.
Sorry,
Sure.
what is the methodology? I want to know what is the methodology for AGI in a slide.
In one slide.
I mean, at least your
Okay. I'll see if I can give you that.
Or even two,
Yeah. I'm doing the preparation talk now. I'm doing the pep talk. You will see it in probably not one, but several slides in a more compact format a little bit later on. Not tomorrow, but next week.
Next week.
Yeah.
Sorry, I wanted to say something about
Sure.
like I wanted to. I heard in passing you said that systems engineering may not be adequate. I would disagree with that, but we can argue about this some other time. And some research that I've done, which was my PhD, I came up. I mean, it was clear working under a positivist paradigm.
Mhm.
And as opposed to the positivism, obviously there is constructivism, which you use in some ways. You've modified or evolved that. So, but the gist is that today, to tackle complex systems, we need to adopt mixed methods. Mixed method means we will use a positivist approach in combination with a constructivist one, or a post-constructive one. So we will use a combination of methods, a range of methods in combination, and that is generally the recipe to crack a complex system development problem. In the same way that the knowledge representation for complex system is not just a single. So you know how you use declarative versus procedural knowledge representation, and when you start working with a complex, so more than a trivial one, you need to adopt both. You need to sometimes represent knowledge declaratively, sometimes procedurally, and then it's the working between the two that makes the intelligent system go further. You know. So I just wanted to add the note that mixed methods is the methodologies that I would see fit. I mean, the framework.
What kinds of systems have you been building?
All sorts.
Not AGI, though.
Well, it depends. I'm here to find out what
Okay.
you mean by AGI, because I do think that I'm working under an AGI paradigm, generally speaking.
Okay.
But because that wasn't clearly defined to a single thing, I didn't know this is why I'm here. So I think I do build it.
Yeah, it sounds like there's some overlap with how we think about this, but there may not be a perfect match between how we use these terms. So that needs to be clarified, obviously, before we can start arguing, which I'd be happy to do,
Some other time.
especially
Well, I just wanted to make the note.
especially if we can learn something from it. Yeah, I'm tempted to ask you what you mean by positives, but we'll hold that thought for now. And I think it's better to wait with this discussion actually until, say, Monday, because I'll have covered some more ground that makes it a bit clearer what I mean, at least. So, as I mentioned yesterday, this is our real modern-day Frankenstein monster. This is a perfect example of the modular approach. And I want to tell you a story. Does anyone recognize this building? Is anyone here a soccer, football fan? Oh, good. Ha! All right.
Why do you call us in London? London?
No, yeah, it's actually, I think it was somewhere outside of London. It's the Crystal Palace. Yeah. Wow, impressive. The story of Crystal Palace, not the football team, was designed and built by this guy in 1851. It was a giant building. It was, in fact, the biggest building to date at the time. And it was built in 17 weeks. That's the power of modular construction, of modular creation. When you can modularize properly, you can make world records, and you can do stuff that no one has ever seen. So, again, I'm showing you this to just hammer in the power of the modular thinking, and that you may be more brainwashed by it than you maybe realized. Now, look at this. It was completely moved in its entirety to another location 3 years later. Have you ever heard of such an event in the history of mankind? It's insane. Now listen to this. Paxton was a gardener. How is this possible? Now, I'm just saying, if you pick the right methodology, yeah, you can do stuff. And the trick that he had up his sleeve was modular construction. So that's a giant story. I think probably it's a unique event in history that something this size has been moved, physically moved entirely to another location. So by picking the right building blocks, in this case glass, steel, and wood, making the windows just large enough that they could be handled by, I don't know how many people, but 3 or 4 or 5, I don't know, so that they could be moved on what I imagine would be medium-sized trolleys, rolled along into their place, and then maybe hoisted up, etc. I mean, these are not small numbers. You could look at the numbers, the actual numbers. You only have 80 people. This is just really impressive. And the glass surface area is 85,000 square meters. This is incredible. So this is modular construction. This is exactly what NASA uses, for example, to build their planning systems for the Mars rover and for, in this case, the Deep Space One probe, which is the first time that an AI system has been sent into outer space. This system actually has some meta reasoning, which is it's an interesting one, and I'll go through it real quickly. But let's look at the modules. This is, again, the blocks. We got the executive module and the mission manager, a planning module, and some experts. This is a collection of experts. They're all coded in ways to handle particular part of a subfield of expertise. Physics, for example, which I'll take an example of. And you've got a system of monitors that's checking the status of things and sending updates to this reconfiguration system. Okay, what did this system do that's worthwhile of entering into my slides? It was used on Deep Space One, which was an experimental probe, to model, to see what you could do with an AI system on board. So they probably had a sticker AI on board, and they modeled essentially the physical, you could call it, body of the probe in software. So there's a complete description in, I think this was Prolog. I'm pretty sure it was Prolog based. So the system has essentially a description of the hardware in software. Now, what does it use this for? Well, it can actually use this to run, to test to see if its plan will work according to the goals. So if it has a goal of, say, opening the solar panel array, or directing the camera to a certain place to take photos of a nearby planet, it can run it on the modeled hardware. Now this is simulations again. It can run it on the virtual model and see if the hardware actually does what the software plan intends for it to do. And so this is what they do and did, and just as an example of what the system did, they had switches modeled. They had everything modeled: motors, physical gears, joints, etc. So the system wanted to turn on the solar panels, open the solar panels, and turn on the electricity from them to power the motors on the camera or something like this. And it opened the solar panels and then turned on the electricity, but the camera did not get power. Okay, a fault is detected. Why isn't there energy coming from the solar panels to where it's supposed to go? So the system started to probe and figure out what to do. It knows that a switch is a physical thing that conducts electricity. This is already modeled in the software. And it has some heuristics that the programmers provided the system with that it can infer that sometimes physical things get stuck because of stiction. So it has another heuristic that says if something gets stuck, try to wiggle it. And it essentially created automatically, this is all not foreseen by the programmers, just the heuristics and the knowledge is there. It made a plan for how to wiggle this thing, the switch, in fact, which is a relay, probably a physical one, I guess, because that's what they said in their article. Although why they would send a physical relay and not an electronic one, I don't know. But anyway, so a wiggling, what does that mean? Well, it gets translated into physical properties, that is, turning itself on and on quickly, rapidly, a few times. And it did, and it worked. And so here's an example of meta-reasoning using meta-knowledge. The system knows that it knows some things about this, about itself, about its body. So it can actually attempt to make a plan to figure out what went wrong there. Pretty impressive feat of engineering. Now, in AGI, of course, why isn't that an AGI then? Well, obviously, it's all just hand-coded by the designers. The system is not designed to acquire any knowledge of its own. Firstly, and secondly, on top of that, of course, it doesn't know that, wiggling something can maybe get it unstuck from experience. It knows it from the heuristics that the designers gave the system. So if something happens, first of all, the probe will not go out of its way to figure out, to play with things. It has no curiosity. And there's a name from NASA. But anyway, it doesn't, go out and acquire that knowledge, and it cannot create these heuristics by itself. So here's another system that is, again, sort of like this grossly modular thing. Now, this is an attempt by some physiological psychologists and neurologists to map out the brain. And of course, the brain is the hardware that runs the mind, and it's hard to, in fact, in the case of the brain, it's hard to separate software from hardware like we can very clearly in the case of computers, because it's really an analog computer. But you see, this looks pretty messy and complicated, and yet we haven't really started to label the arrows. We have only very gross names for these. I guess if you look up some of these, you'll find dozens and dozens and thousands of pages on research on these, even if it's condensed to just the current truth. But still, look at how messy this is, and we're obviously at finer granularity than the few modules that you'd see in typical software programs, but still, this gets pretty nasty pretty quickly, and people try to use modularization to make sense of things. But if you continue this exercise, breaking these things down into smaller boxes with more fine-grained names, so stimulus response connection that one might be replaced by an equation, possibly, or a long list of if-thens and equations. pattern activation. Well, that's some sort of a program. It's not simple. I mean, so it's a real question, you know, how far we can stretch the modular approach. Here's another one. This is my own. This is part of a dialogue system that we built, which is the first system that learns to take turns properly without interrupting the speaker at inappropriate times. It is mostly about sound and not so much about meaning, but it's modular, so we essentially have kept expanding this and adding more stuff to it. There's a real complexity wall that you hit after if you double the size or triple the size of this. There's always something broken that doesn't work, so you spend all your time. Now this was built pretty much by one full-time person and two part-time and implemented. But after a while, after this grows big, you spend all of your time tracking down problems. It just doesn't run. Why? And then you think you found it, and then something else pops up. And why is that? Because this is a system that's supposed to run in real time. It's supposed to work properly based on time. It's supposed to take into consideration the clock on the wall. So one problem we had in building this is that all operating systems that are available, at reasonable cost to us in a research university have fairly long pipelines till you get down to the clock on the computer even. So if you're writing your program in a standard language and you call, the time now, it may be several milliseconds off. And you don't, it's in fact hard to synchronize clocks. This system ran on 3 computers because we just couldn't afford a big fat one that could run it all at once. And to some extent it solved the problem, but it created other problems, mainly the connection transmission of information problem. So anyway, but even if you had all of that solved, there's another layer on top of that, which is the semantics of the system itself. And so we started using messages with very long names. So whenever some data had to be somewhere else, you could look up the trace, the history of it. See, this was sent by that module at this point in time. And now this is on millisecond level, so it's timestamped. Everything's timestamped. And you can see when it arrived in this guy, and then you can see how long it took to figure out that, that should result in that message, etc. I mean, this is even this is before I started the constructivist way of thinking. This is where I had brought this modular thinking. Essentially, none of the systems engineering software engineering books that I found were really adequate, so I invented this. This is actually pulled from subsumption architecture and other areas of AI. So it's really an AI-focused system, but we are using this now to model the growth of the human heart. So it's not a bad idea, it just doesn't scale very well, and it certainly, I'm absolutely convinced of this now. This is not the way to get to AGI anytime soon. There was a little bit of learning in this system. You had one tiny little bubble here doing some learning. So it actually adapts to the speaker. And the longer it talks, it only takes like 2 minutes of talking with a synthetic voice, through a microphone. The voice, the computer's asking you questions and listening to your replies. So you could imagine that this could be used as an interviewer, automatic interview, like, "Hello, this is AT&T. We would like to ask you about our service." And then instead of having a human, you would have a computer doing this. And I'm not going to get the Oscar any day soon. But, and then you, and then you listen, or the machine listens to the human giving a reply to some question. And the question is, when should the system ask the next question? It's a very simple scenario. Well, people hesitate in their speech. They do stuff like this pause that I just did. And currently, computer automated speech systems, they can't handle that. They really can't handle it. It's not just that they handle it badly. They have a timeout. So if there's a silence that's below some threshold, noise threshold, for longer than, say, 400 milliseconds or 600, it's typically in that range, the computer will just assume you're done. So instead, what we have is better information about the prosody. And this controls the system's inferencing as to trying to predict whether you're actually going to continue or not on that same note. So anyway, the learner will adapt this whole system to ask properly the next question in about 2 minutes of interaction. So it's very fast, and it worked really nicely. Yeah, I think I'll jump over that. That's so. Okay. What's the number? So have about 10 minutes more or so, then we'll take a break. So the constructionist methods that pretty much all of AI and all of computer science uses fail because the massive complex dependencies when you're trying to build a system like the one we saw there from Kostlin and Koenig with the cognitive scientists diagram there. You get these dependencies that have to be hand-coded. So, for each of these connections, there's an API. And the API has to be defined by the programmer. And for a big system, of course, there's going to be a lot of these APIs. And they're always changing because as you build the system of any decent size, you change your mind about how it should be designed. And so that's why it takes so long to build airplanes. And that's why there are so many iterations when you build airplanes, because you can't afford the airplanes to falling out of the sky like people seem to accept computers crashing all the time. So to build a big complex system properly, you have to take the aeronautics approach and have lots and lots of iterations sort of the full thing, and prototypes and computer models, etc. And it all goes through maybe 10 times more cycle than your average software program development cycle. You have all these dependencies between modules and between parts of your system. And these dependencies, this is why the boxes become big. Because the boxes are a way to reduce the number of APIs that need to be shared by more than a small team of developers. So you have, 6. If you can make a box that's managed by 6 people, implemented by, something of that order, and you can get away with designing your whole architecture based on that, you've got 20, 30 people working on a complex system. That's a good size. Projects that have hundreds of developers, we have examples of this. There's open source systems that have that. They take a lot more time, and they're a lot crappier, typically, unless there's a really amazing leader, perhaps, or two, and so on. So anyway, these may seem to be very practical, kind of mundane concerns in an AGI Summer School. But really, you can't get away from it. This is what I'm saying to you. You have to ask yourselves these questions. Basically, you want an AGI at some point. The only way to get there is via, as I called it, simulation or modeling of an intelligence system or some. And it has to be runnable, because that's how you check if the system works. If you have a complex system and you can't run it, you're going to sit there for years trying to imagine if this actually works, if this design works. You have to have it runnable. So you can't get away from these seemingly mundane, how long does it take, how many people, etc. questions. It's just unavoidable. So with this kind of an approach, there is no way that the system would actually ever automatically be able to program one of these modules on its own. Now let's say you have even a moderately self-programming system, i.e. it's a system that you designed by hand to handle indoor environments, let's say. Okay? And it's way more powerful than the Roomba vacuum cleaner. It can do all sorts of things indoors. Now, if you say, okay, tomorrow you're going on a plane to the Amazon, or let's say next week, you get a week to study up on the Amazon, the rainforest, okay? And then this system is going to go to the Amazon. Now, it has to figure out how to survive there. For each of these modules, you've provided it with some knobs and dials. So it can ask sort of a status summaries, and it can set these knobs in different ways. These are tunable parameters of your whole system. Maybe some of them, maybe you have a management module that can figure out patterns of these and learn from that. But in any system that is capable of cognitive growth, that is, to develop significantly on its own, that is, for example, to learn better, and to learn to figure out what kind of learning and responses are relevant in what kinds of environments, then this is not the way to do it, because this system will never write one of these modules. So automatic construction of new modules is prevented by constructionist methodologies. Also, automated routing of complex data, because you've got this API defined between the modules. It's hand-coded, and it's coded in programming languages that are meant for human intelligence. So you're trying to implement a human intelligence in a machine, and in order for this system to get there, it has to have human intelligence to use the programming language to reprogram some parts of itself. Well, then that's a tautology, and you've come full circle. So it's not going to work.
So, what was your solution?
That's why I will tell you about the constructivist ideas that we have developed and have resulted in the AERA system. So the divide and conquer, as it's implemented this way, fails. The way that divide and conquer has been done in software to date, and I put this here, at least in its most naive form, because, again, I'm not saying the scientific method, or this is a central part of the scientific method, is wrong. I'm just saying the way we've implemented it for various systems may not, and probably does not work for general intelligence, because it really is holistic. You've got a lot of components, as you saw in the diagram there with the neurologist trying to label the various functions in the brain. You've got a lot of heterogeneous functions whose input and output is vastly incompatible with each other if you do it this way. And you've got hierarchies that may change over the system's lifetime. Hierarchies are, of course, a way to organize, to structure knowledge and to structure information. And if you believe the cognitive science / computational revolution, you also believe that, or at least find it plausible, that we can build intelligence in a machine. So in the known examples of intelligence, the connections between functions, let's just use that term, are massive and they're messy. So if we say, okay, that's holistic intelligence, calls for whole models of mind. I already said this before, but I'll say it again slightly differently this time. I think we'll break now for about 20 minutes. So, let's see, so what time is it now? 3, let's be back here at 3:40. Oh no, it's 3:24 already, okay. 3:45, okay? We left off here. Basically, I was saying that holistic intelligence is what we're interested in. And that's just another way of saying something I was saying yesterday, which is that we have to be very careful at what we exclude when we try to use the divide and conquer method to simplify our task and describe or define stepping stones on our way to AGI. And I want to talk about something now that I call transversal features, which is functions that are necessarily going to have to be available across the whole architecture that we develop. Whatever our system does or is geared towards, if it is aspiring to AGI, to be an AGI, then I believe these transversal features that I will talk about now are really necessary. They're not sufficient, but they're necessary. And so we cannot just ignore them. Okay? And the three main ones are learning, attention, and temporal grounding. So everything that an AGI does, if it's to be operational in a time-constrained reality, which essentially is everything. Everything is time-constrained. It's very hard to imagine any task or usage of an AGI that would not, to some extent, require the AGI to pace itself somehow. This is really central to Pei Wang's thesis, which is the system always has insufficient or incomplete knowledge. It must always make a guess to some extent. For example, I may want to go to my attic to get my snorkel and swim trunk and so I can go snorkeling. Now, the stairs up to my attic may be old. I know that if I fall, I may break a leg and thus not be able to go to snorkel. So this will cancel one of my goals. Also, it will make me not achieve another goal, which is to stay healthy, and another goal, which is not to feel pain. And these are fairly conscious and explicit goals that pretty much everyone has, although we may not think about them every day. You certainly think about them if you're crossing really intensive traffic. So anyway, I will not spend all afternoon checking if the stairs up to my attic are safe today. I will just make the assumption, since I didn't hear any creaks yesterday when I went upstairs, that it's still not broken and that the stairs will not fall down when I'm at the top, and I will not break my leg. So I may not have sufficient grounds to actually make the assumption that I can get safely up and down to my attic, but I still do it. I mean, look, we would all be completely paralyzed otherwise. So this is really a key fundamental aspect of any intelligence worthy of discussion, at least in this room. I haven't talked too much about attention. I will do that in a separate session as part of a session. I think it's the Monday one, or maybe it's tomorrow. I forget, but you'll see. Anyway, I venture to say that achieving this in a complex architecture, doing this transversally, that is, for the whole architecture uniformly, is impossible using modularization techniques, constructionist design methodologies. Now, I just bear with me for a second, because there still may be doubters. I know for sure there will be doubters when you take this story to the outside and you tell people. People are very quick at coming up with counterexamples and making objections, because you're really threatening something that they take for granted and have been studying maybe half their lives. So we could make the counter-argument and say, well, this is the strongest counter-argument that I could think of. Now, look at Crystal Palace. Look at how well modularization worked for that. Even today, doing that thing, moving that kind of a large building from one place to another 3 years after it was built, is completely out of the question. So you see, already it's a very strong argument. What if Paxton had sat around? He was a gardener. So what if he had sat around and waited for self-constructing principles to arrive on the scene? Maybe he would wanted to spend his life figuring out how to invent self-constructing principles, like the same principles his plants use. And so he could just engineer this building to grow on its own. Isn't that what you're saying by throwing out our current best methodologies for software? Well, look, he would still be waiting, if he was alive, that is, if he had done that. And that is ridiculous. So it's also ridiculous for AI. Don't sit around or waste your time trying to figure out principles of self-construction or self-organization. Well, and then I would ask, if we agree to that, then possibly we are saying that cognitive growth is not possible in AI systems at all, or practical. But I think this will become a bit clearer later on. Now, here's the counter-argument to that counter-argument. So here's a forest. Now, let's just imagine for a second that intelligent systems like that implemented in our brains is a bit closer maybe to this kind of a environment or system than to the standard engineering practices today. This is really what we're saying. If you want to take constructionist methodologies to a forest, what you're saying is, hey, let's take our hammers and okay, well, that's a cartoon picture. Maybe if we upgrade it a bit and get more real. This is what this is hardly an amateur tool shed, is it? Well, look, it doesn't even matter if we have power tools. It's just, you see how completely idiotic the match is. We're going to build a forest with power tools, with these kinds of tools. It's ridiculous. So I say the obvious way to create a forest is to grow it from seeds. But that's pretty extreme, you say, because that means we have to come up with principles of seed design, some sort of DNA-like or self-growth principles, biologically inspired maybe. We have to invent or discover principles of self-construction for artificial systems. This does not exist to any extent to speak of. So we're saying, okay, we need principles for seed design, we need principles of gardening, and we need principles of life or self-growth, how to make systems grow by themselves. Okay, now put that thought in your heads for a second. Keep that thought. This is a theme we'll come back to a lot. Characteristics of intelligence. Okay. We all agree that intelligence is a product of the operation of a complex system with a complex architecture. I don't think that's in any dispute, except for the people trying to find the relativity theory of intelligence. It's not a big group, but they do exist. So the study of intelligence is the study of systems. We're trying to reverse engineer a system that already exists. We understand how it works. Some people will say, well, we don't have to reverse engineer the human brain or any animal brain. We can just rediscover, basically, just as nature did. We can rediscover the basic principles, and they don't necessarily have to be like nature figured it out. It doesn't even have to have any similarity to it. Well, there are certain similarities that you can't really get away from, like we're interested in some of the effects that intelligence has, like coming up with good ideas. And if you cannot ask questions, good questions about a problem, then you're not very likely to come up with good ideas, because of all the things, you're not going to think about everything in the world. You're going to have to, an intelligent system or a system of some sort that's supposed to come up with good ideas must select some subset to process. So that system must be able to ask questions. Well, if it's supposed to ask questions, it has to be able to formulate, categorize, and organize some information, and make some plans about how to acquire missing knowledge, etc., etc. So it's very hard to make the argument that an artificial intelligence is going to be vastly different from human intelligence. No, it's at the high level, it's going to have very similar properties. It's going to have, and I will go through this, attention. It's going to have learning, etc. So anyway, intelligent systems are heterogeneous, large, densely coupled systems. The fact that, for example, drinking too much beer will slur your speech. Well, this is maybe not something we need to replicate in AIs, but maybe it tells us something about how the learning of speech happens and why that particular chemical combination results in that. It's very strange how it's, seemingly very different parts of human existence seem to influence some other parts, distant things. And I think this issue is very well characterized in the fact that we can make analogies between almost anything. And we can very quickly, if you ask me to make an analogy between two concepts or two things or whatever, I can very quickly tell you whether I'm going to come up with a good one or not. And so it's fairly strange. I mean, so analogies is actually another thing. It's not in our current plan for presenting to you in this summer school, but it's definitely one of those transversal functions that I think I'm hard-pressed to ignore. As we talked about yesterday, for picking starting points, maybe I don't think analogies is a good starting point for AGIs. I don't think that if we think long and hard about how to implement analogies in a computer, we'll figure out how to do AGI. I'm not so sure about that. But it's definitely better than many other ideas that people have had. I won't take any examples now. So, and of course, the ultimate transversal function is self-inspection, knowledge of self, and learning about your own learning. You know, you say, okay, well, I'm asked to do this or that. I know I don't know too much about these things. I'm going to need at least a week. I'm a slow learner. I'm going to need a week to, or not to break chalk. I'm a slow learner. It'll take me a few days. You know, obviously, I broke one today already. So it's going to take me more than a day. How do we do this in a system that's growing and learning things that the designer did not anticipate? So intelligence is a lot less like this than this. This is not the right model for doing AI. But this is how everyone's doing it. Well, to build an intelligent system, we're going to need some modules. We're going to have instructions for how to put it together. We know that when we turn on the ignition, when all these parts are assembled, that the engine starts up as long as there's electricity in the battery and gas in the tank. And then we know that if we put it in gear, because of the causal structure of the system, it's going to take off when we let go of the clutch. This is a bit different, and it's much more, it's uncomfortable to me because I don't really like gardening and I kill all the plants that I come in touch with. But it's slowly dawning on me that it's a better way, at least for the next decade or 2 or 3, I don't know. It's a better way to think because the current methodologies are so grossly inadequate. And I know there are some disagreements with that statement here today, and I'm looking forward to the discussion. Because if I'm wrong, you know, I don't want to spend my next 10 years. But actually, you'll see some evidence that I might be right before the summer school's over. So I'm a lot better off than in 2009 when I really formulated all of this nicely enough to write a paper on it. Now we have some evidence. But yeah, so these are the main things I want to talk about as far as transversal functions. I just want to go through them a little bit more. So learning, of course, people can learn an enormously wide range of things. And what are we comparing that to? Well, what I'm thinking of there is, for example, compared to current machine learning or even to other animal species. Attention is a bunch of stuff. It's a very useful term because it kind of gets at the heart of the kind of thinking we have to do. Have you ever come across an AI system where the author claimed that it had some attention mechanism? Anyone? Good. Which one?
The Libra system.
Yeah, okay. So you're already, I think we already found an AGI-er here. That there was a 0.
What was the answer?
The LiDAR system.
Can you tell something about it?
It's not my system, and I haven't prepared to do anything on LiDAR. There's plenty of documentation online.
What does it do?
It's an AGI aspiring architecture.
Linked from my introduction to AGI. one of the system in my list, so you can follow that. Okay.
We did some study of the attention mechanism in all of the major, let's say, and widely published architectures, AGI aspiring architectures, or architectures that have been discussed in the same sort of, within the same scope of things, and compared to what we think when we think, you know, my attention was elsewhere, or you know, what we think of human attention. The currently implemented attentional mechanisms that exist are really only worthy of being mentioned as, okay, we've started on that. But none of them, I venture to claim, can make any claim to be anywhere close to the kind of role that attention plays in human intelligence. And then, of course, temporal grounding. This one is pretty much ignored completely. But humans are very good at this. In fact, I had a slide projector once where to go forward, you had to hold down the button for 100 milliseconds. But to go backwards, you hold it down for 160 milliseconds. And at first, it was really annoying, but I got the hang of it once I realized what was going on. It didn't come with instructions. So I said, why is it going backwards? I sat there for maybe 20 seconds or so, not 20 minutes, 20 seconds before I figured out, oh, it's the timing. But that 60 milliseconds was not so hard to learn. It's horrible human factors, obviously. Don't use this ever. It's like, oh, I meant to brake, not to hit the gas. I was 60 milliseconds off. It's like, so it's interesting how, and how did I learn that? I knew it must have something. Well, here's reasoning. I knew it had something to do with the button because I wasn't touching anything else on that remote. Of course, had I played with that button for a while and not figured it out, I might have looked elsewhere to see if there was another button I was accidentally holding in or something. But how did I figure that out? Well, I used my mental faculties. I ignored the TV for a little bit, and I ignored, you know, some people talking for a little bit, and I focused on this thing. It was harder to interrupt me at that time. So attention is really a controller on our resources. And it's really meta-control in a way. This is one of the things that I think we can do a lot more interesting stuff with than nature did with us. I think that's actually, yeah, that could be, once we get to build an architecture that's powerful enough and interesting enough to actually implement attention, then we can start to play with a lot of interesting ideas for how to do attention differently than nature does. And also, you know, doing more parallel things and having the mind split itself up and doing stuff in parallel as two separate minds, but maybe with less interruptibility each, or various things like that. But we won't go into that too much. So remember, transversal functions, these functions affect every perceptual, cognitive, and motor skill in natural language. And that is a strong hint that it's a good idea. Doesn't mean that we have to have it in our ultimate AGIs, but it sounds to me like it might be a good idea to be able to do if we want it. Also, the level of detail that we focus on, like the temporal detail that I was focusing on with this slide projector, you know, here we're, you know, I didn't know if it was the strength of pushing or the timing or whatever, what it was really. So what did I do? I did some experimentation. I varied some parameters. It wasn't very meditated. It wasn't like, oh, it could either be this variable or that variable. Let me see if I can vary this one without touching the other one. Or maybe it's 4 variables. And it wasn't like that. It was more like curious, playing around kind of human way. Pretty much like we all acquire knowledge all the time, and especially children. So the level of detail of temporal resolution can vary quite a lot using attention to control it. Here's another very important thing, that all these features, all these functions that are transversal also affect knowledge of self and of our own mental operation. Not perhaps as deeply as we can ultimately have it in AGIs, but it does affect it to a large extent. So, now, for any given environment or a range of environments, these functions have had some time to evolve. So, for example, when I'm playing tennis, which I don't do often, but it happens, I'm used to playing tennis on courts where I don't have to worry about cars. I don't have to worry about model airplanes hitting the ground or hitting me in the head, etc. And I can lower the threshold in my head my mind can lower the threshold, or actually heighten the threshold at which point my game gets interrupted by such events. Now, the risk, of course, that I run is that if someone's playing with a model airplane and this tennis court is outside, then I'm more likely to be hit by a model airplane. But again, these are calculated risks we take, and we modulate the usage of our own minds based on all of these factors all the time. So my attention is getting trained. It's not like the attention is a controller on top of it and it just comes with its predefined DNA program that, here's how you implement it. No, the attention, even the whole thing is getting trained. So when children are growing up, their attentional mechanisms are being trained. That's why it's so useful for kids if their parents want them to become, something in particular, like a tennis star of the future or a rock musician or whatever, then it's good to get them to play that violin when they're 3 rather than 30. It's because of this. The system is growing. It makes the system more capable of adapting to the environment. So the system is programming itself. You've got these functions. Even the learning, if you go to school early in your life, you get better at learning. It's not like that just that you learn better, hopefully, but you actually also are better at learning. You're being trained to be a learning machine. And so that's why we have compulsory education. Okay, now, so this is really my conclusion here. I don't care really if you're completely convinced or just willing to listen. That's all really I require, is that you're willing to entertain this idea. Because that's all that's needed for us to go through the ideas that I have in the remainder of my lectures. Let's see. I'm not getting a lot of questions. I'm sure there must be some questions here that you're itching to ask. Yes?
I was just curious, in terms of this modular approach that you were discussing earlier, if there's been researchers in AI in the past that have attempted to replicate human-level intelligence using a modular approach and have failed?
Well, everyone, pretty much, by and large, is heavily based on and trained and based on this world of modular thinking, because all the software that's available, unless you write your own programming language and your own operating system running on your own processor, you're in some way tied to this modular thinking. And in fact, the processors that are available today are, to some extent have built in this problem, although it tends to be more of a software and OS issue, that getting to know the actual clock, so you have some sense of the progression of processing, it's hard to do it properly. Did I hear someone raise their voice there? Okay. So I think it's hard to get away from this, in fact, because it's everywhere. And so, yes, I guess the short answer is everyone. Everyone is trying to use this, and everyone is failing, because we don't have AGIs yet. The hard question now is to figure out, what it seems to be the most promising route to get out of this problem. And we also, unless you want to get involved with the military, it's hard to get proper funding, which is why most of AI research is supported by some sort of military funding.
I'd say
Yes?
general remark,
Mhm.
which is, I don't think we can progress with AGI completely. Speculatively, yes, we can do what we want. That we can come here, learn, not achieve anything, and still be happy that we met and whatever. But if we want and need to progress AGI, which I think there is a need for, and I'm sure there's a lot of great ideas coming out from various bits, we do need to take a step back and address the fundamental question, like what is intelligence? However philosophical this discussion may end up becoming, we need to find some answers that we're all reasonably convinced with. Then we can start making a plan on how do we go there. And it's very complex. I mean, because we are on the verge of doing something which is intractable, impossible, which cannot even be conceptualized at the moment. And therefore, if we need to make any progress, which I hope we will, given time, we need to have a roadmap. And I think I remember at some point in 2010 there was a roadmap. Is the roadmap for AGI still something that people are following, or? I remember attending.
There was actually several.
Yeah, that's what I'm saying.
Just now we still, as I explained the first day, we still don't have agreement on what is the goal and what is the final path.
Yeah.
And some people actually suggest that at the beginning that maybe we should try to reach a consensus on that, and then everyone work together toward that goal. But clearly, it's not going to happen very soon.
Okay.
Just because there are very different opinions, and also, as I mentioned, each of them actually is justified to a certain degree. It's not, something you can clearly say is completely wrong.
Mm-hmm.
So it's very, very early, and so I think maybe it's more healthy. At least personally, I think it's more healthy to encourage multiple approach to be explored in parallel.
Sure.
And of course, at the same time, to encourage people to cooperate if they share enough ideas.
Yeah, because definitely a multiple approach should be encouraged, I agree with that. But to have some common understanding of what do we mean by AGI. So for example, what I found useful was the list of requirements. I don't know how good that is, in the sense that we don't know how valid, have we tested, have you evaluated these requirements? I don't know, it doesn't matter, we will. But now, I could look at the systems that I'm developing and I say, do they meet these requirements? Maybe even half of them. It could be like a half AGI system that I'm doing. So that was useful. These are the requirements. Is there any disagreement that these are not AGI requirements, or that there should be more?
I have no idea. Frankly, these are fairly recent, as in sort of the last 4 years. These requirements that I presented, have been at the forefront of my work for maybe 4 or 5 years
So
only.
there's a paper.
So yeah, there's a couple, well, not really. Not a good one.
So, I mean, because if you publish the paper saying these are the requirements, then at least people can write another paper saying, no, I disagree.
Yeah.
So then at least people would have something.
Yeah, no, but it's too early for that even, because these requirements have been created in view of a goal that we wanted to achieve. But as Pei was saying, some other people say, okay, well, that's not the goal we want to achieve. We want to achieve this one. And starting to sort out requirements for either one and compare it is just too early. And I think that's probably one of the reasons.
And so just to finish this comment in general, taking a step back to what I was trying to say yesterday, if we do want to achieve AGI, we need to be able to define it in some way. But understanding why the purpose behind the universe, or at least this kind of similar, very high, ambitious goals, it could be necessary. And we may not be able to achieve AGI unless we understand the purpose of life and the purpose of intelligence in itself.
I hope that's not the case, because I think that's a pretty hopeless task.
I don't think so. I think it's,
No, I think everyone can.
it's an essential task without which
It's pretty much a religious question to me. I mean, I can see, and frankly, people have already answered this question for themselves, and in groups. Yeah,
answer.
yeah.
So, but there is no agreement.
Oh no, and I don't think, I don't see any way to reach an agreement, and I don't see any reason to necessarily have to reach an agreement on that high and abstracted topic for intelligence. Because if I fast forward 100 years in my mind, then I'll see, that some avenues turned out to be better than others for achieving certain goals and sub-goals of those goals. And you can make a map of sort of, well, if you wanted to do this or do that, then this path was obviously better, and but another one was better here. I think what is frustrating for me as an AI researcher for over 2 decades now is that it seems like people don't really ask themselves this question about methodology at all. And if I go to my colleagues and say, okay, well, do you aspire to an AGI sometime in your lifetime, or some of your successors? Is that like an end goal of some sort, or a stepping stone in your path? And they'll say, yeah, probably. So you think your methods that you use currently will get you there? They will typically say yes, but they have no clue about it. But even even many people say, well, I haven't thought about it. And I said, well, why don't you? I don't care, because I just like artificial neural networks or fuzzy logic or whatever it is, and that's what I want to spend my life on. And then they spend their whole life, having defined their own work in terms of a tool, and they always talk about the tool as if it will lead to an understanding of a phenomenon that clearly, at least to me, is completely irrelevant to. Almost completely irrelevant.
But this thing of, we could even have, again, hypothesis. Group A that thinks that the purpose of life, or this is the definition of intelligence, and therefore AGI will develop according to that. And then we could have another definition of intelligence and a subset of AGI that could develop according to that. So it doesn't mean that we cannot have different ideas, even
Right.
different ones within the same. But
Obviously.
I do think that being able to define intelligence in a slightly more formal way, however difficult or paradoxical that could be, it is essential. Otherwise, we will make progress, we will learn things, but I'm not sure whether we're going straight for what we are hoping for.
I'm not sure sitting around waiting for philosophers to come to an agreement, because that's a philosophical issue, One of the things I really like about AI is the fact that everything seems to be mixed together, especially in AGI. You have, psychology, philosophy, and computer science, or I should say maybe cybernetics, rather, all sort of mixed together, sitting on top of a decently mature field where, computer science, where at least you can start to argue more cogently than just by writing papers. You can actually write code and run things and argue a little bit more strongly your point of view in 2013 than you could in, say, 1913. But but I think the range, just as I'm not a big believer in sitting around and waiting for, say, the right math or philosophers to agree on the definition of intelligence or whatever. I mean, philosophy had hundreds of years of talking about intelligence, and a lot of the ideas that came out of philosophy were because of people talking about intelligence and thinking it was one thing with which I and most people maybe today disagree. But so, we should do something. But the annoying thing now, that thing that hampers us from really understanding this phenomenon of intelligence, I think, is in large part, a methodological one. And unless people realize that we need significantly different methodologies, at least I'm convinced of that. It seems to be the common view of AGI researchers. A majority of AGI researchers, at least in the AGI Society, seem to agree on this, that the principles by which you develop traditional AI methods are insufficient. So I will give you just a glimpse now of how we are thinking about, my group is thinking about this. And but first I'll take one question here.
So there's a wide spectrum of attempts to measure complexity, from Kolmogorov complexity to logical depth and time-bounded Kolmogorov complexity. And what do you think are the most useful measures in the context of AGI?
That's a brilliant question that I myself have asked several times in the past few years and come up with very bad answers to. So I'm not a complexity theorist, and I'd love to get a better answer than is available, but I haven't found any. I have some ideas now, but it's way too premature to tell you. So, but it will be very useful once we get better measures of complexity, the kinds that are useful to us, because then we can start to talk about comparing architectures and better.
Do you have any suggestions on ways to think about it, even if you don't have an answer ready?
Well, no, let's not go there. It won't be worth your time right now. Maybe after 2 beers tonight or something. Okay, so this then is something we end up with, but when you use this architecture concept, this concept of architecture, of course, it comes from physical buildings. This is an architect probably drew this building. In fact, many of the buildings here are not the work of engineers. You can tell that they have some artistic insight, and I'm hard-pressed to believe that pure engineers came up with them, because engineers tend to be way too utilitarian in the way of thinking. Architects don't think so much about money, or they see value in some of the citizens finding something beautiful, and they count that in their equations. So anyway, however that happened, we have lots of buildings here. This is architecture. We adopted this to computer science, so now we have software architecture, and it inherits that kind of heavy feeling of concrete and glass. So the kinds of architectures that we are talking about are, think back to the trees there. It's much more like biology. A cell has a particular architecture for how its chemical reactions happen and how it sends signals, how it senses that a cell is near to it, etc. This is all implemented in chemistry. But there's an architecture to cells. They may be blobby and not straight and certainly not heavy, but they can do pretty heavy-duty stuff, like growing into a human heart or a brain. And so that's the kind of very flexible architecture, the architecture of intelligence that we're thinking about. And we really are talking about this old idea that the whole is more than the sum of the parts. You see the formula there. Probably haven't seen that before. I searched for the formula. I couldn't find it, so I had to. Anyway, that's the formula. So we're going to have to bring some ideas from that are more common in, say, biology and some of the more soft sciences, which is self-organization. How do societies work? Why do we have so many groups of people that have organized themselves? Yes, true, most societies have an actual geometric boundary that they call their country, and then they have rules, and the rules only work up to that boundary. After that, it's someone else's rules. Yeah. The equivalent, I don't know if the equivalent exists in biology, probably. Probably, yeah. If you take fairly different species, you probably have a similar thing. This happens through self-organization. Societies just happened to form. It wasn't like someone on the outside said, hey, we're going to have these societies on the planet. You see sort of proto-societies in groups of animals as well, depending on the species. But these are principles of self-organization. There's something in the operation of the whole as opposed to the individual elements that when they come together, they do stuff that kind of wasn't obvious or foreseen or is somehow meta. If a Martian came to Earth and found a single individual and studied it to death, don't take that too literally. I didn't mean to kill the poor guy, but basically, they would study it forever and ever, and it would be very hard for them to come up with the concept of societies. That's my thought. Because if you think about a software program like Keynote or word processing program or something like that. Let's say you have a laptop that's running a word processing program. A Martian comes along who wants to understand how that program works. They have a non-invasive mechanism for looking at the processor, and they see all these logic gates. And they could study that processor forever and never come up with the concept of a word as in a natural language word like you have on the screen here. It somehow exists at a different level of abstraction. And it rests on the underlying foundation, but it adds more. Now, in self-organization, the principal mechanism is feedback loops. So, where the feedback is on the system itself. Now, it may be different parts of it, but certainly for, say, an embryo growing, the cells somehow figure out at some point that, okay, now we're in a group together and let's form a heart, and so on and so on. And so you have fairly seldom hearts forming in toes, although it does happen that the program gets messed up. But it's been probably 20 years since I saw the first photo of a fly that had an eye on its wing. And basically, they had figured, this was one of the first genetic engineering experiments, they had found the program for an eye in the fly's DNA. They just cut it out, copied it, and then they figured that basically there's a pointer of sorts in the DNA that says this program should be run here. So they put it on the wing, and lo and behold, the fly got the eye on the wing. It didn't see with it because there were no neurons running to the brain. But, so these are programs. The body has all sorts of mechanisms to knowing that it's at this stage versus that stage, and it's figuring out sort of, is it time now to start developing that part? Puberty being an example of this time delay, and so on. Now, Piaget, if you know Piaget, he proposed that our mind develops in stages. Brilliant idea. Doesn't live too well nowadays. It seems it had all sorts of problems and shortcomings, but the fundamental idea was great because you can sort of imagine that the reason that you can't, for example, my nephew until age 3 or so, you couldn't use double negatives, and I think that's actually, if I studied the psychological literature, I'm betting that we'll find this with every human baby, that before the age of 3, roughly, they can't handle double negatives. But then suddenly they can at some stage, and it's roughly around the same. So this is the kind of things that, who is familiar with Piaget? Okay. So Piaget, I would call him a psychologist. Some people call him a sociologist. I don't know if he was classified as a philosopher. I have no clue. I really don't care about these labels. The idea was good. His implementation of the idea, basically, it doesn't look like his stages were that mapped that well onto reality, the proposed stages that he claimed to see. And it's not necessarily clear that even the experiments that he based this on are that repeatable. Well, they're repeatable if you do them like he did, but if you change the wording, because these are experiments with human children. For example, a famous experiment is you've got a glass this tall and narrow, and then you've got a glass this wide and low, and you pour the same amount of liquid in each. The water goes up to here and there, and you say and you have the child watch the water comes from 2 jars that have the same amount of, that look the same, have the same amount of water. You do this, and you know that it's the same amount, and you say which glass has more liquid, and the child will always point, until some age, I forget, will always point at the one with the taller water line. But it turns out if you word the questions in a certain way, and I don't remember the details, then you don't get that reliable distinction anymore or result with the children. They will maybe say they're equal or whatever, but so you can the mind is a complex thing. How are we doing on time? Okay, got 15 minutes. So, all right. So I'm saying, basically, we need some new concepts, and I'll explain to you what I'll give you one example of how a feedback loop matters in our case. So, if you have an architecture that's supposed to develop somehow on its own to maybe reprogram some parts of its functions, let's say these are not modules with APIs anymore, but these are these boxes represent functions of some sort. Okay, got these functions, various functions here. the system itself should be responsible, pending its input from the real world, to improve or change, typically improve, but sometimes just change to get ready for something else, its own operation. Well, then you need new kinds of mechanisms. And let's see, I want to give you an example of a chemical feedback loop that gives you, that surprises. It's called the Zhabotinsky, Belousov-Zhabotinsky cocktail or soup. So, yeah, maybe we'll get back to that one. It's a fairly complex reaction, but the result is very surprising. If you have this mixture of chemicals in one liquid solution, over a period of only minutes, you get these kinds of patterns. It's like strangely Chinese. I wonder if they came there before us. It took Belousov, who was the first to discover this. This was in, my history is not so good, in the first half of the 1900s. He discovered this. He sent this to several chemistry journals for publication. They all said, "Ha, baloney, we're not going to publish your paper." And for 10 years, he tried to get it published, and they just dismissed it. Obviously, none of the editors actually created the cocktail in their lab. Otherwise, they would have said, "Wow, cool," and published it immediately. So Zhabotinsky came along and actually, I think it was like 12 or 15 years later, managed to write it up in such a way that it did get accepted and published. So this is, so when you start talking about feedback loops and what happens, actually the cool thing is if you, okay, so this is if you let it sit. If you actually have this in a glass and you shake it, then the liquid will just change color every 20 seconds or so. Yeah, like all at once.
So he just happens to mix these things together.
I don't know the history of it. Yeah, I think that's in fact what happened. Another example of the power of feedback and interaction of rules, which, you know, that's what this is, ultimately, because we understand the chemistry, so it's just a bunch of rules. We can do some experiments with cellular automata. This is 100 by 100 cellular automata, one-dimensional, where each cell here is operating according to the same set of rules. And you start this out, this out with, say, a random set. So just give the cells a random state at the outset, the same number of, same rules, the same set of rules. What are the rules? Well, in this case, in this example, we have only 5 rules. Turn brown if there are more than 20 green cells around you. And lifetime, which is you've been brown for 30, I think, exceeds 30 steps. Or actually, and turn brown if there are less than 12 green patches around and lifetime is more than 20. Turn brown if the number of green patches around equal 25. So that's like an exact number. Turn brown if lifetime under any circumstance exceeds 60. So after you've been around for 60 cycles without changing, when green, then turn brown. So, and then brown, if you're brown, now there was red and gray there also. Those are static, actually. Those don't change. when brown, turn green if there are more than 8 green patches around and their lifetime combined exceeds 80, and there are more than 10 brown ones around. Okay? Within, I forget what the range is, something like 10 or something like that. 10 by 10 around each cell. So each cell looks 10 by 10. And you start out, say, randomly like this. The gray and red are, forget exactly what the rules were for that. But no, actually, those are also, okay. So I'm missing some rules. Those are fairly simple because the main rules that matter here are the brown and green. So what happens after about 200, 300, 400 cycles is that you get these waves. These waves are actually moving. It's like a shore. Just from those 5 rules. It's very surprising. Now, in this particular case, this is just a random case out of a number of experiments we did in the past, just playing with these things. And you can, of course, also have meta rules. So, and that would be more like biology and probably like intelligence. So you have rules about which rules you follow. So, you could have that triggered by saying, if you've followed these rules for too long, go to that set. Or if too many of the cells around you seem to be playing by these rules, use that rule, etc. And so you can imagine, the complexity by just a very small set of rules that can be created. And that's one of the fundamental ways of thinking in constructivist AI. So now this is really the fundamental concept that we will carry with us forward from now on. So we are thinking along the lines of self-constructive artificial intelligence systems with general knowledge acquisition skills. So they can actively create goals, steer their processing, and control their processing in light of their experience and in light of those goals. They start out with a seed specification which is much, much smaller than their ultimate state, eventual state, whatever you want to call it, fully or semi-fully developed state. And they're intended to be adaptive to a wide range of things. So they must be able, just like the child that gets better at tennis because they start earlier to play tennis, they can adapt their mental faculties. In fact, they can reprogram themselves to some extent. We're not talking about full reprogrammability because, as you could see with only those 5 rules, starting out with, say, 1 million rules, trying to predict how that system will turn out eventually when it programs itself running in reality, that's going to be probably an impossible task. We'll never go outside of a particular box. This is, because we want these systems to operate in practical situations. We want them to do stuff in our environment, let's say. So you wouldn't want them to pose as big a threat to us as, for example, genetic engineering, which is much more dangerous than AGIs will ever be, because the number of interactions and complexities introduced when you genetically engineer an organism and then release it in nature is just vastly, vastly bigger than an AGI that's maybe trapped in a robot body or controlling the internet, let's say, even for that, or the electrical system, even for that, it's not so hard to imagine ways to build a box like this. But for the planet, if you release an agent that is capable of self-programming, that is evolution, then that may have unforeseeable results. Just to put that in perspective of some sort. So just a few more slides and then we're done. In our approach, we are targeting something like 10,000 atomic elements. That's the atomic operating units, the smallest unit in the system. Now, in a human-written program, that may be the instruction, line of instruction maybe, or the class, depending on how you want to slice it. But in our case, we're talking something similar. That is something along the lines of a line of code. Now, typically, programs don't change. Atomic structures in standard software are typically the class. And typically, the system has all of the classes available already and will never change lines of code, will only make instances, let's say, of classes, and then kill instances of classes and so on. And in what we are targeting, the system itself actually writes lines of code, and it must therefore be able to interpret lines of code, because if it's to be self-programmable, it must be able to understand its own code to some extent.
What kind of abstraction is it? Is it like assembly or logo? Or?
It sits somewhere between assembly, let's say, and Prolog. We won't go too deep into that because we tried that last year in Reykjavik, and frankly, we were not happy with how little people took from those sessions. It just can't be. I mean, everything about our programming approach is different from what you're trained to think of. And so it takes at least a week to just cover the full thing to a depth where people can start to see, sort of have an overview of the differences themselves, not to understand it, so just to understand what needs to be understood, So we're not going to do that. We have our programming language called Replicode, and there is some information available online on it. If you want to check it out, I will write the name here. But just trust me, you don't want to spend too much time on it unless you're really planning on delving in for the next few months, okay? I've had trained engineers study this for weeks and come crying, okay? So, this really gets to a point where we have to say some things about our programming environment, because basically all programming languages have been designed for humans. And if we want a system, an architecture that programs itself, the semantics of these languages, just like the semantics of these big blocks in the architecture, is too complex for automatic processing. So we need simpler semantics. We need programming languages with simpler semantics, programming languages that are essentially made for us humans to just ride the seed. Just write the seed and then have the system run itself. Now, we may do some gardening. We will move the pot to a bigger window or whatever, and and maybe do even a bit more than a gardener would typically do, at least for the next decade or so, until we have it really figured out. But that's the essential idea. You write the program. The designer writes the seed and then gives the system the proper environment, and come back to the simulation environments for training these systems. You put the system then in an environment where it can start to acquire its own knowledge. So just a few more slides here and then we're done. The reasons for why the code needs to be self-inspectable for self-programming, it's kind of obvious at face value, but just breaking it down a bit further. In order to be an effective programmer, the system must be able to predict the effects of its changes to its own code. So not only must it be able to predict the effects of its changes, but it needs to have some way of at least understanding why these changes happen, and also have some idea of the side effects. This is just like when we do planning. If I want to get to the top of a mountain and I decide to climb straight up, the implication may be that my hands are going to be bloody, and I may be out of breath, and I might die getting there because I'm out of food. So there are side effects to all actions, and certainly there's no exception for self-programming. So when you're trying to improve for example, the way your attention mechanism works, well, it's not you really. I mean, when your mind is growing, and as a result of you deciding to train yourself playing tennis at an early age, the mind has to have some ways of measuring its progress. And it's actually it's kind of a top-down, bottom-up thing, because when, and this is maybe where emotions play a role, because when we get angry at how bad at tennis we are, what the effect of that is essentially that to focus our attention on how we're doing it now and what's wrong with it and how we could do it better. So it's our mind sort of emotion system making the attention system control our resources for that problem. This is why it's so important to be able to control your emotions if you want total control of your life. As any father of a 4-year-old knows all too well. Okay, so one way to achieve this, I'm not saying it's the only, but this is the way we're taking, okay, is to do this. So basically, it's not sufficient to understand the effects of things you do in the world, like, this or that, or throwing something. You also need to understand the effects of your own thoughts. So, the AGI must have some way of figuring out that if it spends a lot of time thinking about this thing, then it will not get to the other things, or whatever it is. So how is it that we can have an architecture where the attention can direct its operations to any part of itself, its environment or internal, and still have it work for the whole system? This is a really tough engineering and philosophical and design question. So one way to achieve that is to say, well, if we had a uniform representation for all knowledge, then it doesn't matter whether the knowledge comes from the outside or whether it's generated in the mind. All operations will work the same. It's just that the source of the knowledge is different. So this is why we have been working on a system that has a uniform representation across its whole architecture. And include in that, so we also look for a uniform size, because the size affects how long an atomic operation takes. And so if all of the atomic operations in the system take just the same amount of time, if they're all the same size, they all take the same time, then it's a linear prediction how long something will take, either mental or a physical task or whatever, because you just count the number of atomic operations it takes. Okay, we did this one already. Pan-architectural pattern matching. Now, I'm just going to touch on these. We may go into a bit more detail on these later. What is this? If you have a system that's growing, i.e. the system itself is managing its own changes and improvements, it needs to understand whether things are going in the right direction or not. It needs also, as it's learning what works and what doesn't, to be able to compare and contrast. I did this with this task. I'm going to try the same with this task. Now I'm doing the third task. What is different, or what is it more similar to? The only way to do that is to, at least for cognitive growth, and you can make the argument that this goes for most things as well, is to be able to take some part of operation. Let's say I'm learning to be better at paying attention to the right things when I'm playing tennis. Whatever it is, let's say this is the attention mechanism. The system that's responsible for management obviously should not be changing at the same time. Will be able to look at the current state, compare this to some other mental faculty and say, okay, well, doing X worked here. There are some similarities. I will try X here. Let's see what happens. I try it. I produce a new version of attention. I keep the old one, or at least the significant parts, and I can compare them to see if it looks like it's going in the right direction. Okay? So pan-architectural pattern matching, you need to be able to take large chunks of architecture and compare it to other chunks of architecture. And now I'm really using architecture here in a very loose way. I could just as well say knowledge. But the knowledge in the architecture here, it's all the same. It's soup. And you compare it, or the system compares its future state to its past state and says, oh, it doesn't look like these methods work. That's a bad idea in this scenario. On top of this, of course, you also have all these other learning methods, mechanisms like trying to classify the world in the most useful way and coming up with conceptual groupings of things, et cetera, et cetera. This is why I really think that AGIs are in a strong need, at least for a decade or more, probably more, are in dire need of being thought of as baby machines, that you essentially start it at some point and you grow it. Because we need to figure out how to make these pattern matching mechanisms and all of these things work together in a system. If we can figure out ways to freeze some things, like, oh, we can freeze this thing, and we can freeze that thing, and we don't have to actually have it evolve. For the next 5 years, we're going to run the system like this. It's going to be frozen. The attention does not have to improve. We have some tasks that we can use to play with this AGI prototype that don't require attention to evolve. Then that's good, because it's less things changing all the time. So it's really, you can see it's still an engineering task. We're just slicing and dicing it fairly differently. And got this. So we had the high-level requirements from yesterday, and now we're adding some requirements at a lower level. So these are the transversal cognitive functions, and these are the main ones. And again, this is the challenge. And I really feel I'm going to end on this one. This is our state of methodology. It's based on the joke that the cow jumped over the moon. So anyway, tomorrow we'll probably have a bit more time to do discussions. So please see if you can reply to my posting on MindMakers. And also feel free to bring some questions on the material covered so far tomorrow. All right? Thanks.